The Bob Murphy Show, episode 87. We've got another very interesting episode here for you folks. I am interviewing physicist Dr. Sabine Hossenfelder, who is an author and theoretical physicist researching quantum gravity and now is working on dark matter and dark energy. She's a research fellow at the Frankfurt Institute for Advanced Studies, where she leads the Analog Systems for Gravity Duals group. And her book is Lost in Math, How Beauty Leads Physics Astray. However, what we're talking about in this episode is not her book, but rather I had read two pieces from her recently, and I thought, I got to get this lady on the podcast. This is awesome stuff. So basically, the first half of this episode, we're going to be talking about dark matter and dark energy. First, just to define what it is, and then to raise more philosophical questions about, hey, is this just a placeholder, basically, for physicists to say, we really don't know what's going on here. The observations don't match our standard theory, so let's invent these new concepts. So we talk about that sort of thing, and you'll get a better sense of what actually happened and the state of modern physics and cosmology on that score. But then also, I wanted to have her on. So those of you who follow my work on the economics of climate change, you may have seen when I responded to it, but I was very surprised to see her article in the New York Times on the climate models. And specifically, the title was, so this ran back in June 12th, 2019. The title, of course, the Times gives the titles. It's not that the author picks it. But the title they gave was, Is Climate Change Inconvenient or Existential? Only Supercomputers Can Do the Math. And so I like this because I thought it was very honest to say that right now, these computer models that are simulating the Earth's climate system, they're open-ended. In other words, they're not, even though we have agreement on the basic equations of the natural laws, the physical laws involved, they have to take shortcuts to yield an answer, a prediction, because the Earth's such a complicated system. And so the point being that these models, their predictions about what's going to happen, even if governments, quote, do nothing, she was saying, range anywhere from an existential threat to humanity down to just a mere inconvenience. So I thought that was interesting that the New York Times ran that, because it seemed like they were implicitly admitting, maybe the state of climate science is not as, hey, case closed, there's a consensus, boom, 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 stop being deniers, as we're being led to believe, at least in U.S. politics. So that's the sort of thing that I'm going to be talking about with her in the second half of the interview. Fascinating stuff. Without further ado, here is my interview with Dr. Sabine Hossenfelder.
Well, Dr. Hossenfelder, thanks for joining us on the Bob Murphy Show.
Nice to meet you.
Just for my listeners, so they can understand your background, can you just briefly explain, what your current position is?
I'm a theoretical physicist and a research fellow at the Frankfurt Institute for Advanced Studies.
Okay, great. And what was your dissertation on, or your doctoral work?
Well, I did make my PhD on physics at the Large Hadron Collider, so I'm a particle physicist by training, but now I actually work more in the foundations of quantum mechanics and astrophysics, so dark matter and stuff like that.
Okay, great. So if we could just start, I think a lot of people, they've heard these terms, dark matter, dark energy. They don't really know, where did it come from? So if you don't mind, could you give us just a brief history in terms of physics and cosmology? Where was it in the 1930s, for example, that this idea was first posited? And can you explain what the observational problem was, and why did this concept even become a possibility?
Yeah, so I'll try to do this. But honestly, this is the talk that I normally give that takes 1 hour. So I'll try to make it brief. So let me first by saying something that a lot of people get wrong. Dark matter and dark energy are two different things.
Right.
They don't necessarily have something to do with each other. So let me just start with saying maybe the obvious. The theory of gravity that we're currently using, so that's Einstein's theory of general relativity, tells us that space-time curves in response to all types of matter and energy that are in this space-time. Basically, by observing what the universe does, for example, expanding, we can tell what types of matter and energy are in the universe. So this is one way that we can establish that there has to be some additional matter and some weird kind of energy in the universe. But this is not how originally the first evidence for dark matter came about. It was, I believe he was Swiss. Zwicky is his name. So I know he's not German, but now I'm not sure if he's Swiss or Austrian. So what he did was he observed a galaxy cluster. So a galaxy cluster, that's a collection of some 100 or maybe 1,000 galaxies that are bound together by their own gravitational pull. And so he observed a cluster known as the Coma cluster. And he basically saw that the galaxies in that cluster were moving faster than he was expecting. Why did he have an expectation for how fast these galaxies should be moving in the first place? Well, that's because the velocity is determined by the total amount of matter that is in the cluster. So you see these different galaxies, you can estimate how much matter you see, and that should tell you how quickly these galaxies move around each other. But this estimate just didn't fit with the observation. So what Zwicky did was he postulated that there has to be more matter in this galaxy cluster, which he couldn't see. Mm-hmm. And he called this dunkle Materie. So that means dark matter.
Okay.
So, and that was sometime in the 1930s. So this is by no means a new observation. But I think that in the first couple of decades, people were more like, there's something that someone has observed that doesn't quite add up. So they didn't really pay a lot of attention to it. But as the years passed, there were more and more observations, notably those by Vera Rubin, who basically saw the same thing in individual galaxies. So you observe how fast the stars move around the center of the galaxy. Mm-hmm. And there too, you see that they move faster than what you expect just based on the visible matter. And again, this is a mismatch between observation and the predictions of your theory. And you can fix it by postulating that there has to be some additional matter in the galaxies that we don't see. So dark matter again does the trick. And so this was, I think, sometime in the 70s. And since then, there have been further other observations that all fall into the same story. There's something that doesn't add up between the predictions of our theories on the observations, and dark matter fixes this mismatch.
So can I use an analogy just for the layperson? Suppose we have a telescope and we're looking at an individual solar system and we didn't see any star, but we saw a bunch of objects that were as big as, let's say Mars, and they were rotating around the central point, but we couldn't see anything there. And so then it would be logical to say, okay, there must be a very massive item in the middle of that system, because otherwise, why would these planet-sized objects be rotating around something? Like they would just fly off into space. And so there must be something there that, even though we can't directly observe it. Is that a good analogy? But so it wasn't at an individual solar system level, but it was at either the galaxy or a cluster of galaxies?
It is similar to that in that we only observe really the gravitational pull. Mm-hmm. Then a plausible explanation for this is, well, there has to be something that is causing this gravitational pull, like in your analogy. Mm-hmm. But of course, there's, the other option is that there's just something about gravity that we're not getting right.
Well, yeah, so and that's what my next question was going to be, so I'm glad you went in that direction. So I think if it were just a matter of, no pun intended by using the word, but if it were just an issue of one area out in outer space that there was this anomalous behavior, but all the other calculations and observations were within tolerable limits of the standard theory, then you'd say, okay, maybe out there's whatever, a black hole or something that we can't observe. But my understanding is now with this theory of dark matter and dark energy, it's something like 95% of the total universe is postulated to be just dark in that matter. Is that roughly correct?
Yeah, two things. One thing that I have to say, I should have said this right in the beginning. This term dark is really, really misleading because it leaves you with the impression that the stuff actually absorbs light, like it swallows it or something,
Right.
like a black hole, right?
Right.
You could say a black hole is dark. But what it actually is, it's transparent. So light just goes through. You can't see it. So, but you know how it is with terminology,
Sure,
right?
yeah.
I mean, dark matter sounds cool, and this expression just stuck. But really, it should be called transparent matter. It's the same with dark energy, by the way. It's not actually dark. It's transparent. You can't see it. So you quote this number 95%. Maybe let me briefly say what this refers to. As I said in the beginning, you can use observations to infer what kind of matter and energy there has to be in the universe. And so you can make a breakdown of this matter energy budget. And this tells us that there's something like 75% or so is dark energy. And then there are like 20-something% is dark matter, and the rest, which is about 4.5% or something like this, is normal matter, like the stuff that we are made of. So this is where this 95% comes from. It's the combination of dark matter and dark energy. If you only look at the matter sector, then you have about 85% of this, which is dark matter.
Okay, so I guess maybe right now is it a good time for you to explain, because in the beginning you made the distinction between dark matter and dark energy. So I think we get how the dark matter, reconciles general relativity with the astronomical observations. What is it that the concept of dark energy, what problem does that solve?
Dark energy is what is responsible for the expansion of the universe accelerating. So it's something that affects the universe on really, really large scales. And it's just observationally, it's a different thing. And also in the way that this problem is solved, theoretically, it's just an entirely different concept. Of course, there are certain theories that say, well, maybe both of them have the same origin. Certainly, this is something that people are thinking about, but it doesn't necessarily have to be the case. They could be entirely different things.
Okay, so that's something, too, if you could elaborate on. So is it a correct statement to say, so the standard theory is that long ago there was the Big Bang, that all the matter and energy was in a single point, and then it explodes outward. And so you would think just normally with gravitational force that the universe's expansion would continually be decelerating. If you didn't, right, just the standard, there's gravity and it should be slowing it down. But are you saying that now they think that at some point in the past, the expansion actually accelerated?
Well, yes, it accelerated in the past, and it will again. Actually, it accelerates right now, and it will continue to accelerate. And this is what dark energy does. So the funny thing about dark energy, and that's basically the way that it is defined, is that it does not dilute as the universe expands. Actually, the simplest case of dark energy is what Einstein called the cosmological constant. It's just a constant of nature. And as the name says, it's a constant.
Right.
It does not change as the universe expands. But here's the funny thing. All the other stuff in the universe, so the matter that we are made of, and also radiation, photons, light, stuff like this, it does dilute as the universe expands. It's just if the volume increases, then the energy density goes down. So what happens if the universe expands is that all this normal stuff becomes less and less relevant. And eventually the only thing that really matters is this dark energy. And dark energy has the effect of accelerating the expansion. So there was a phase in the very early universe that is often referred to as inflation. At least a lot of, cosmologists think that this happened. There's some little fine print here that maybe it was not actually this way, but that's how the current story goes. So you had this phase of inflation that was an accelerated expansion. Then this ended. Now, then there was a matter-dominated phase, and then at some point, the density of the matter and radiation becomes so small that the cosmological constant takes over, and then you get this accelerated expansion. And if it's really a cosmological constant, then this is just how the universe will end, basically. It will continue to expand and expand faster and faster, and that's that.
Can you give us at least some intuition, if perhaps the actual details are too technical, but how is it that we are pretty confident that the expansion of the universe is accelerating? Like how do we, in other words, it's not that, 100,000 years ago, humans measured the expansion of the universe and now we're doing it right now and it's speeding up, right? So how is it that, how do we know that? Like what observations do we see that the acceleration is the hypothesis that explains the observations?
Yeah, that's not how it works. So actually, this difference in the acceleration between now and 100 years ago is entirely negligible.
Right,
on the cosmological, because we're talking about billions of years. Okay, so 100 years, you can forget about this. No, what we do is that we use that the speed of light is finite. So we can look back into the past if we observe galaxies that are very, very far away. So what we can do is we observe the light that comes from these distant galaxies, and it has traveled for a long time. Again, we're talking about something like a billion years or stuff like this, through our universe. And so if we measure this light right now from galaxies at a variety of distances, we can infer what the universe did in between. And so what you need for this is, of course, you kind of need to know what kind of light was emitted at the source, because otherwise you could just see, well, any variation that we see, well, maybe it was a different thing. And this is where certain types of supernova become very important. This is what the astrophysicists like to call standard candles. Because they have a fairly regular pattern to them. So if you observe them at different distances, you can tell what happened in between from a very old supernova to a younger supernova. And the only way to explain these observations is that there has to have been a cosmological constant that caused an accelerated expansion. There was a Nobel Prize for this a few years ago for this supernova observation.
Okay, so let me paraphrase that. So if light were instantaneous or virtually instantaneous in terms of its speed, so that when we looked out, we were just seeing the distant stars or galaxies as they are, quote, right now, all we would be able to tell, like if we took an observation today and then took an observation next week, we would really just be able to see how they're moving today. We wouldn't really have a sense of, is the expansion faster or slower than it was a billion years ago. But you're saying because light is a finite speed, when we look at something a billion light years away, we're actually seeing the motion of that thing a billion years ago. And so with that trick, there's a sense in which so is it close? I mean, I realize this is a little bit perhaps inaccurate, but is it something like we're looking at two galaxies that are close together a billion light years away, and we can see how quickly is the further galaxy moving away from the closer one? And then we can look at two galaxies that are close together 2 billion light years away, and we get a sense of how that change in the billion years is affecting the acceleration?
Yes, one thing to say is that there's your question, like what will we see if the speed of light was infinite, is very complicated, because basically general relativity wouldn't work at all.
Yeah, sure.
so that's a really hard question to answer. But loosely speaking, what we see is the difference between how the light travels from two supernova at different distances.
Okay. So just to summarize, then it sounds interesting. Is it that for some observations, it looks like it looks like gravity's too weak. In other words, like you see galaxies rotating around a central point, and if all the matter that were there is the directly observable, stars and plasma or whatever, then the speed, the rotational speed, they should just be splitting apart. So it seems like the gravitational force is stronger to hold them there. And so the only way to explain that, if general relativity is correct, is that there must be transparent matter that's also there that's creating additional gravitational force. But then it's almost like the opposite problem when it comes to the expansion of the universe itself. You would think it almost looks like there's that if general relativity is correct, and that's the only thing, then the expansion should be decelerating, and yet it's accelerating. And so the way to fix that is to posit dark energy.
Yeah.
Okay.
Right.
So I guess and then like we said, these aren't just little rounding errors. This is huge. Like when you try to reconcile everything all together, it's something like 95% of what we think exists is this transparent stuff. And perhaps only 5% is the stuff that we directly observe. So especially since the two, in a sense, are like, do you know what I mean when I say like they're opposite problems? That the one, it seems like there's not enough mass, and on the other one, it seems like gravity's too weak on the one hand, and that's what we need dark matter to explain. On the other hand, it's almost like gravity's too weak.
Yeah, I
too
wouldn't
strong.
say opposite. They're just different.
Okay, they're different.
Things.
Yeah.
They do different things. Yeah.
Right. So I guess, are there some people who posit that these are just placeholders? These terms, dark matter and dark energy, are just placeholders for our ignorance, and really it's just maybe general relativity is not correct, and that's what's going on here. And if we could just find a better theory, then the 5% of what we could observe would be consistent with the observations.
Yes, there are certainly people talking about this, but these are actually different theories. So one has to be a little careful here. So dark matter and dark energy are not just placeholders, as you put it, but they actually have very distinct properties. So I previously said that really dark matter should be called transparent matter, so the term dark is not particularly helpful. But that it is called matter does not just mean, well, it's any kind of stuff.
Right.
But physicists actually mean something very concrete by the term matter, and that's not an empty statement, because it means that if you want to fix this mismatch, you can use stuff that behaves pretty much like normal matter. And that's a very simple explanation. So that's the great appeal of dark matter, is that it's just parametrically a simple explanation. At least that was the original idea. Okay, so again, there's some fine print here that says, well, maybe it's actually more complicated than people thought it is. But at least that was the idea. And it's the same with dark energy. As I said previously, the simplest case of dark energy is just the cosmological constant. So that's a constant of nature. It's hard to think of any explanation that can possibly be simpler. But as you say, there are people who are pursuing an alternative explanation, which is that there's something about gravity that we're not properly understanding. And then, there's the question, like, which of the two explanations is actually the better one? And this is where it becomes really, really complicated, because you have to ask, well, which actually fits all the data better?
Right.
So people are still fighting about it.
So presumably nobody has yet discovered an alternative theory that explains it better. Otherwise, that would be the dominant theory.
Well, it depends on exactly what you're asking. So there is a body of theories that is known as modified gravity.
Okay.
That's basically not gravity the way that Einstein taught us that it works, but, well, it's modified, right? So, and you can write down theories for this. And these theories actually work better than dark matter for galaxies. So if you're only looking at the galaxies, then modified gravity does a better job. But of course, as I said earlier, we have a lot of observations for dark matter that come from very different scales, like from the galaxy clusters. And then I didn't talk about this, but there are observations from gravitational lensing and from the cosmic microwave background and from the large scale structure. So there's galactic filaments and all that kind of stuff. And if you look at this, then modified gravity does not to be working does not seem to be working all that well. Or in some cases, one just doesn't know how to make such a prediction. So the theory is not up to it, or people don't know how to solve the equations. So you see, the question, like, which one is the better theory, depends on exactly what kind of data you're looking at.
Okay, great. Just for the benefit of our listeners who don't know too much about this, I mean, the reason general relativity is the presumptive theory here is that it did outperform Newton's theory of gravity. There's things like the orbit of Mercury and such, right? That Einstein's general relativity made certain predictions that were better fitting the observations than Newton's original law of gravity.
Yes, general relativity is an extremely well-confirmed theory, and Newtonian gravity has its limit. It's a good approximation. Like if you want to calculate how an apple falls from the tree, stuff like that,
right.
You can use Newtonian gravity. But once you're dealing with objects that have large relative velocities, or you have a strong space-time curvature, like black hole horizon, that kind of stuff, you need to use general relativity.
Okay, so I'm wondering, is the following? Are these a series of true statements that, depending on what class of phenomena we're studying, physicists have a theoretical mechanism that explains it very well? So if you're looking at the subatomic level, they've got, quantum electrodynamics, and that does it very well. If you're looking at the solar system, or perhaps several solar systems, standard general relativity does a great job. But then without postulating dark matter and dark energy, general relativity doesn't, quote, work very well when it comes to much bigger distances.
Yeah, that's right.
So, I mean, is it possible? And again, I'm just curious, like, what people are looking at. Just as, hey, we've got quantum physics to explain the subatomic level. If you're at a bigger scale, then general relativity is what we use. Is it possible then that just means, okay, for something that's even bigger scale than the solar system, we use something else, not general relativity, just like quantum physics? It works great at the subatomic level, but it's sort of impractical or harder to apply at the solar system level. Is it possible is there something like that maybe the next evolution would be different theoretical mechanisms depending on the scale?
Yeah, so this is what modified gravity is supposed to do. It's just that we don't actually have the theory.
Right.
So
okay.
And also I have to say that we know just observationally that it's not at a certain distance where the deviation from general relativity becomes important, but it's at a certain acceleration, odd as this sounds. So if the acceleration is too small, if you go out in the galaxies to the far distances, then the acceleration that is acting on the stars from the gravitational pull becomes smaller. And we know that at a certain acceleration, there are these new effects that start kicking in. So it's not at a specific distance, but it's an acceleration.
Okay, it's just that in practice, to get to that level of the acceleration, you're going really far out. So, Okay, gotcha. That's great. So can you, I know this is one of the areas where you're working in. So I think you've been somewhat critical of these alternate, like they call MOND.
But I'm kind of critical of pretty much everything.
Okay, yeah. Well, so am I in economics.
The thing of so MOND stands for Modified Newtonian Dynamics, and that is basically an approximation to whatever is this theory of modified gravity that people are looking for. But actually, I'm not really critical of MOND because it works very well for the task that it was designed for. It works well for the galaxies, for the rotation curves. It's just that we know already that, strictly speaking, MOND is wrong. It's wrong the same way that we know Newtonian gravity is wrong, because it's just an approximation. Or to put this more formally, MOND does not respect all the symmetries of general relativity. So strictly speaking, it's incompatible with general relativity, which does not work. Okay, so but phenomenologically, if you just look at the data, basically, and you want to have a curve that fits the data, then MOND does well. So there seems to be something true about it.
Right.
So that's the one thing. But as I said previously, you can't use MOND to say anything about the cosmic microwave background. It's just not in the regime of applicability. No one really knows what to say about it. So for these cases, you still have to draw on dark matter. So on the other hand, I'm also critical of dark matter, in particular when it comes to galaxies. There are, the thing is that a galaxy is not, it's not like an atom or something. Atoms are all very regular. They are all pretty much the same. We have these 120 different atoms that are in the periodic table, and that's pretty much it. But galaxies are all one of a type. So really, if you want to predict what a galaxy does, you have to do rather complicated computer simulations. And so there are a lot of, a lot is maybe saying too much, but say half a dozen to a dozen, depending on the size, computer simulations that study the formation of structures in the universe and also galaxies with dark matter. So all these computer simulations work with this dark matter paradigm. And for a long time, for 20 years or so, they have consistently found that the result of these simulations do not fit with the data. Mm-hmm. Okay, so what have people done? Well, they haven't said whether maybe dark matter is not the right explanation, but instead they have improved their computer codes by adding additional parameters. Until now, we are at a stage where these computer simulations actually do reproduce the universe pretty much the way that we see it. So, and that's all well and fine, I really like these computer simulations because they produce beautiful visualizations. So It's hard not to like it. But one has to be very clear that these are no longer predictions. These are computer codes that have been tuned until they reproduce what we observe. So then you can no longer say, it predicts what we observe, right? And so what I find peculiar about this is that it takes such a huge amount of effort to get the galaxies right with dark matter, with all these additional parameters that you have to add and all these astrophysical processes. When MOND, can do this basically with one parameter, it's one equation and it does the job. Mm-hmm. And this makes me think there has to be something true about it, something that this dark matter idea just doesn't capture. There's something really missing in this dark matter paradigm that MOND gets right. So personally, I think that the right answer is somehow a combination of both.
Okay, great. So I think some people who are familiar with the history of physics and astronomy, this what you just said there, that might remind them of like in the Ptolemaic model and how they had the famous epicycles. And so, they're going around in circles, but maybe there's circles within the circles and so on. And so are some people like, does that memory ring true to some people that it looks like yes, ex post, we can just keep fiddling with it to get it so it works. But it's not that was some pure simple theory that was there from the outset, that we just after the fact twiddle the dials to make it fit the observation?
Yeah, it's very much comparable to this. So one has to be clear here, though. It's not that there's actually something wrong with trying to fit observations by amending a model, but the issue is that the biggest appeal of this dark matter explanation was that it's a simple explanation,
right?
And now with adding all these epicycles, it becomes increasingly less simple. And then you have this alternative explanation that is MOND, which is a very, very simple explanation. So just parametrically, MOND is vastly preferred, at least on galactic scales. So and then again, we're back to this complicated question, like how do you decide which is the data to look at to draw conclusions about which model is the better one?
Okay, so I guess as we wrap up this discussion, because I want to ask you about your New York Times piece on the climate modeling in the last half of this interview, but I guess, so if you had to summarize, can you just give us your general thoughts on, like, do you think physicists, they have a pretty good command of the forces of nature here, and it's just a matter of, tinkering with it? Or do you think, is it possible that 50 years from now, they're going to realize, wow, there was just this much more elegant theory that it took this genius to discover, this team to discover? I realize that might be an unfair question, but do you understand?
I hope it will not. I hope it will not take 50 years because
okay.
I hope to see it in my lifetime. No, I think that whatever is the right theory will turn out to have properties of both dark matter and modified gravity, and this is or dark matter and MOND, because that's a theory that we already have. But that's an option that no one actually wants to study because people fall into either of these camps, but don't want to split into both camps. So that's my perspective on the matter. And I certainly hope that with increasingly better data, it will become increasingly obvious that dark matter alone does a crappy job.
Oh, okay. So that's interesting. So is there hope in your mind that as we get better telescopes and think that there's just gonna be a lot more raw observations to work with, and that'll help guide?
Oh yes, well, this has already happened because people can observe now a lot of galaxies, types of galaxies, like the very dim galaxies and galaxies that are very far away and all that kind of stuff that just was not possible 20 years ago. And this has certainly taught us a lot about the predictive power of MOND, for example, because MOND fits all these new observations quite well, whereas dark matter has had big difficulties accommodating these new observations. So, and then it happened again, what you just said, that people try to fix the theory.
Okay, so the last thing I want to just clarify to make sure I understand it. Are you saying the workhorse versions of MOND right now, they don't rely on any form of transparent matter? They just take observed, I call it classical matter. I don't know if that's the right term, but standard stuff that we observe that people in the year 1900 would have recognized as such, and that's all it uses. So it just has different equations describing the force of gravity at those scales.
Yeah, that's how MOND works.
Okay,
yeah.
Okay, great.
It's basically you postulate that at a certain acceleration, the 1/r² law of gravity just becomes a different law. That's literally how it works. It's kindergarten math.
Okay, so sort of like, is it a good analogy to say Newton's laws were a decent approximation as long as the velocities weren't close to the speed of light? And so the same token here, that general relativity was a decent approximation as long as the acceleration wasn't too large. Is that a fair way of putting it? I guess does MOND mathematically
wasn't too small, so general relativity works well at large acceleration. But yeah,
but MOND works at smaller acceleration.
Yeah.
Okay. All right, very good. So now we realize we're running out of time here. I did want to ask you, it caught my eye, on June 12th of 2019, you had an opinion piece in the New York Times. The title, I realize they probably gave the title here, but the title they gave was, "Is Climate Change Inconvenient or Existential? Only Supercomputers Can Do the Math." And then the subtitle they gave is, "Accurate Predictions of Earth's Warming Require Computers That Are Too Expensive for One Country or Institution." So can you just summarize that's a very provocative title they gave. Can you just summarize what your argument was?
I didn't write the title.
I know. I write stuff
usually
too.
Works. Well, I want to put ahead. I told you this earlier. So I'm not a climate scientist. I interview people about this kind of stuff, and at least I'm a physicist, so I understand a little bit of the papers. But yeah, so basically the message I'm conveying is what I have learned from talking to people in the field. And so what I'm writing about there is an idea that comes from a group of climate scientists who have basically realized that to make better long-term predictions, they need more computing power to get the grid size down to a kilometer or something. And this is just something which currently no nation is able to finance. I actually think it's not a question of being able, but of not having the will. So they have this proposal that we need an international center where everyone all over the world could draw on the results of these computer models to make better, in the sense of more accurate long-term predictions for the climate trends. And I think that's a very sensible thing to do. And I'm somewhat shocked, actually, that they were not able to get this funded, because in if you compare it to the amount of money that we will have to spend on adapting to climate change or on mitigating climate change, then this is really peanuts. And you want to have these better predictions to make decisions about what to do, right?
Right. So can I add, so just for some of the technical detail here, I forget the pronunciation. Is it Navier-Stokes equation? Am I saying that roughly correct?
You're asking the wrong person.
Oh, okay, yeah.
Something like that, yeah.
So let me say what I took you to be saying, and also because I've done a bunch of research myself on this. So so sometimes cynics will say, oh, those climate models, they just, turn the dials to, it's sort of like what we were saying about the, the dark matter, that they can just, refine the models to match the previous observations. But I have seen the people who create these climate models, they say, well, we're constrained by the laws of physics, so we can't just say anything, that the model has to respect the laws of physics. But my understanding, and I think your article also alluded to this, is that, the Earth is a very complex dynamical system with, water and atmosphere and clouds. And it's really, there's a lot going on. Fluid dynamics is famously difficult to model. And so even if we thought we had the exact correct equations to describe the basic forces, we couldn't actually solve it. We couldn't do a simulation of the actual Earth's climate system with this, solar radiation and everything going on. And so they have to make approximations and so they divide the Earth up into large grids, and then they sort of do approximations of what happens inside that grid, rather than, they obviously don't model it down to individual molecules and things like that. That would just be way too complex. And so that's number one, why different computer simulations yield different predictions, is because the way they decide to make the assumptions to take like computational shortcuts, because the underlying equations are too difficult to solve right now with existing computing power. So is that?
So the issue is not really that the computations are too difficult. It's just that it would take too long.
Okay, it would take too long. Yeah.
So it's really a matter of how well can you make these computations on the hardware that you have available. And so that's exactly right. So one of the major reasons that the long-term predictions of the different models diverge. If you've seen this graph. In the IPCC report, then you have this shaded area, right, where the predictions diverge from each other. So by the year 2100, the average warming could be anything between 2 and 5 degrees. This is what this headline referred to. Like, is it existential or a mere inconvenience? So these 3 degrees make a big difference. So you really want to know better, and at least that's my perspective. And it makes a big difference how the different models treat the processes on the scales that the models can no longer resolve. One of the biggest issue, for example, is certain types of clouds. They just have to make certain assumptions about how the processes in these clouds work, but these are not actually computed from scratch on the machine, because it's just it would just take too long. So getting down the resolution of these computer models would very plausibly, you cannot actually know exactly before you've done it, but it would very plausibly bring down the discrepancies between the predictions of the models. So this would give us much more information about what we have to expect, and therefore also would give us information about what to invest in, how to deal with the situation.
Yeah, so again, I'm an economist, but I do a lot of work on the economics of climate change. So yes, when I first got into this area, this is, 10 years ago or so, I started reading the IPCC reports. And what my conclusion was, and I'm curious about your reaction, is I thought, okay, this isn't like a hoax in the sense that, these climate scientists are all part of this big conspiracy. But what I did think was the confidence with which they reported their results was vastly overrated. In other words, they were leading the public, or at least some of the more outspoken ones were leading the public to believe if governments don't do X, Y, and Z, we know for sure that these awful things are going to happen. And I thought, no, really, like with my understanding of how you're making those predictions, there's a lot of uncertainty involved in those calculations. So I thought they were, at least some of them, were misrepresenting the degree of confidence they could have in those predictions.
It's probably true that some people have overstated the confidence of the predictions, but at least the people that I've been talking to have been very clear that, they're always talking about a distribution of possibilities. This is basically, it doesn't have anything particular to do even with climate models, but look at any model in any area of science. The only thing it will give you is statements to a certain level of confidence. Right. So there is a certain distribution of possible outcomes in the next 100 years. And you have to, and this is where the economics part comes in, you have to ask, how do we deal with this uncertainty? How much risk are we willing to take? And where do we invest our money to handle this risk? And to make this assessment smartly, depending on what your values are, of course, you want to have a good assessment of this uncertainty. And certainly better, more accurate predictions will help you to do that.
Okay. Yeah. I'm also wondering, too, would that, just to try to link the two topics, is that one of the stumbling blocks right now in terms of cosmology? Is this the computing power? Like, Are certain of the rival theories that are offered to explain these astronomical observations as part of the problem? They can't actually crank out the implied predictions, that it just takes too long to solve the model, or is that not really a problem in that area?
I don't think that this is currently the main problem. So it's certainly true, that these people are also running their codes on supercomputers, and it takes a long time. So, but that's pretty much where the similarity stops. I think that right now in cosmology, the biggest question is really how to combine all the different types of data that we have, and not only look at the galaxies, and not only look at the galaxy lenses, and not only look at the cosmic microwave background. So you have all these isolated areas, but you have to find a way to compare the goodness of the prediction of one model to all of these kinds of data. And so this is an area where I think that the software development is right now actually much more important than just the brute computing power. And I actually think that machine learning will do a lot to advance this area, and we're currently seeing the beginning of that.
Okay, well, great. I guess this last question I have for you is for people who are interested in these ideas, or if they want to follow you and your work, can you point them to some resources? Like where can they find you, and or if they want to learn more about these issues?
Well, I'm in the great position that, for all I know, I'm the only person with the name Sabine Hossenfelder. So if you want to know anything about me, you just Google my name, and it will bring up, everything from my personal homepage to my YouTube account to my Twitter feed and my blog and everything. It's not complicated.
Okay, great. Yeah. Also, folks, if you go to bobmurphyshow.com/87, that's this episode number. I'll also put some links, Dr. Hossenfelder, to your website and so forth. Well, thank you for your time. I thought this was a fascinating conversation, and good luck on coming up with that theory that solves the problem of the observations.
Thanks for having me.
Okay, so long.